we go. So here are the two scenarios that really comprise all of calculus. Which one are we working on right now? A or B? What do we know to start with? How fast something is changing, the rate of change, and we want to build the accumulation function from that. How much of it there is at any given input. Okay? So that is integral calculus. That's the road we're on right now. We're developing integral calculus. And so let's be more specific. So this is the very biggest picture of what we're doing. You know how fast something is changing. You want to know how much of it there is. So let's get a little more detailed. So you know how fast something is changing. What do we have? We know how fast something is changing. What is it that we have that tells us that? An exact rate function, right? Exact rate of change function. And then we want to know how much of it there is. What is our goal? To build? What are we trying to build out of that exact rate function? Exact accumulation function. That's how much of it there is. Question is, how do we get there? What's our roadmap to get from exact rate to exact accumulation? How do we start? How do we start? We've got exact rate of change. Yeah? Oh no, you're jumping right to accumulation, right? What do we do first? Steps. Wait, go ahead, Nicholas. We make a pretend rate function that has constant rates. We make a pretend rate function that has constant rates. That should feel very familiar. 2 weeks now we've been doing this. Okay? And then from that, now that we have constant rates, we can use the math of constant rate of change and sum up bits of change for each constant rate. K delta x, K is our constant rate over the interval. We sum up these bits of change. Now we're totaling up, we're accumulating, right? How do things accumulate? Bit by bit by bit. Okay, and so then from there, we want to develop an exact accumulation function. That will be the last thing we do. We haven't gotten there yet. Okay, we haven't gotten there. All right, so how is it that we get from exact rate of change to exact accumulation? We use constant rate of change. We form step functions. The step function, the pretend rate function, and then K delta x gives us bits of change that we can add up. And we can track it as we add it up. That's building an accumulation function. So it's all about constant rate of change. That's why there was a whole module. All of module 2 is on constant rate of change because that's the key to getting from exact rate to exact accumulation. All right, so let's keep looking at this here. So our exact rate of change function, R. From that, we built the approximate rate of change function, the step function. And then from that, we build the approximate accumulation function. That's this bad boy. And then the last step in the journey will be to get from the approximate accumulation function to an exact accumulation function. Again, we might start talking about that at the end of class today. So I want to focus. This is really, there's a lot going on here. So we don't want to rush through this. I want to take most of the time today to keep thinking about what's going on there and apply it to an example. Okay, that's the handout that you have. So before we do the example, let's focus on, this is step 3, the approximate accumulation function. Let's focus on what is going on there. Okay? So before I start the animation here or the slideshow, take a minute just to get get yourself oriented to what you're looking at. So have a conversation with the person next to you, identify everything on here, and make sense of what you're seeing just right here. Take a minute to talk about this. Go. That's what we're trying to figure out. All right, where's Sierra Rose? Sierra, tell me one thing, just one thing that you observe about what's going on here. Anything. A of x is the rate of change. A of x is the rate of change. What do you think? Let's see. Tianyan Green? Tianyan Green? Okay, how about Trevor Hatton? Trevor, what do you think? A of x is the rate of change. Agree with that? What's that? No. So tell me something you disagree with that. Well, correct that, or tell me something that you observed about what you're looking at. Negative 0.5 is a starting point. Starting point for what? Where we're going to start doing what? Finding rates. So in the end, what is A of negative A equals negative 0.5? Where we're going to start accumulating, right? So that's the x, the input value where we want to start accumulating. Okay, did you want to add something? Right. So yeah, it's going to be where we start looking at the rates. Why? Because it's going to be where that input value, where the accumulation will start. Okay. Tell me something else. Jonah, Malloy. Where's Jonah? Okay. So if you don't respond, it's like you're absent. Okay. Katrina. Where's Katrina? Tell me something else. We got the starting point of accumulation is negative 0.5. Tell me something else. What's that? Right now, for the current value of x, left of x is 1.5. What do you think? Yeah, that's true. Yeah, so if we plug the current value of x in, we would get the left of x would be, right now, would be 1.5. Good. Can you tell me something else? What was that? Yeah, can you tell me one more thing? Go ahead. So you were going to say something next year. Go ahead. Okay, she said there's 4 whole intervals. So in this from A to the current value of x, we've got 4 whole intervals. True, good. Matt? Delta x is 0.5. Good. What else? There's lots of things to observe here. Yeah. To calculate what? So say it again. To calculate how many intervals? X minus A over delta x. And then take the floor function of it, right? Yeah, and that would give us 4. So if we took that current value of x minus A and then divided by delta x, that would give us 4 point something, right? 4.7. If we took the floor of that, we'd get the 4. Good. What else? Yeah?
The first step is right at or about 0.39.
Okay, yeah, so the first constant rate for the first full interval is about 0.39. And is that an amount of accumulation or is that a rate of change? 0.39.
It looks like it's starting the accumulation.
0.39 is the starting value of accumulation. Agree with that? No, this is a rate graph, right? Everything in this graph is rate of change. The exact rate of change function is r. That's the curve, and then the steps Are those accumulation or rate of change? That step function. Approximate rate of change, right? It's pretending to be R. The steps are trying to pretend to be R, so they're rate of change as well. Another one.
A times j minus 1 delta s is going to give us the number of full intervals from a to x of the j.
Okay? Yeah, that's right. Good. Brock, were you going to say something?
R of 1.5 is the rate in the current interval.
R of 1.5 is the rate in the current interval. So how relate that to x. So what is R of 1.5 related to x? The current value of x. So you said R of 1.5. Relate that to the current value of x. How does that relate to the current value of x, the R of 1.5?
It's the constant rate of the x in this interval.
Right. So at x, the pretend rate is R of 1.5. The pretend rate at x is R of 1.5. One more. Did you have one more? Okay. So now watch. Here we go. So now we're going to talk about that formula. Here we go. So the total accumulation from Q from A to X means, what does it mean? It means the accumulation of Q across many completed or whole intervals, and that's the first part of the equation, right? The sum of this whole thing right here is, what is that whole thing right there? That's just an input value plugged into R. And that is k of the jth interval. That's the constant rate in the jth interval. R of this expression is the constant rate in the jth interval. And then this is delta x. So what is this doing? This is summing up a bunch of k times delta x's. Do you see it? So it looks complicated, but you got to be able just to see the big picture of it. That R, blah, 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 and you should know what the blah is, we're just not going to focus on it today, is the constant rate in the jth interval. So for what I'm showing right here, this is the third interval. This value right here would be K3, the constant rate in the third interval. Times delta x gives what? So what would K3 times delta x give you?
Delta y?
No, it would be the rate at 1.5.
It would be the rate. So K3 times delta x gives the rate. K3 times delta x. So this rate, whatever that is, 0.4 or whatever, times delta x gives what? What is that?
Delta y.
A bit of accumulation. A bit of the accumulation of Q. A little bit of change of Q. All right? So the total accumulation of Q from A to X means the accumulation of Q across many completed whole intervals. In this case, 4. Plus what? Plus the accumulation of Q across a partial interval. Starting at left X to X. So R of left of X is, we'll call it K star. Because it's not one of the J's. The J's are the completed intervals, right? J equals 1 to the number of completed intervals. But then we have this last constant right here that's blue. So we'll just call it K star. And that's R of left of X. And then what's this? X minus left X.
Delta x is delta.
Yeah, so that's that distance in this. It's a distance less than delta x. X minus left of x will be that distance of that yellow right there. So we'll call it delta x star, because it's not delta x, it's less than delta x.
It is.
Okay? And so what is that? What is K star times delta x star? Tell the person next to you. When you multiply K star times delta x star, what do you get? Tell the person next to you. Okay, you should have said it's a little bit of accumulation. It's the little bit of accumulation for this last little part from left X to X. It's the accumulation of Q across the partial interval. It's a little bit of accumulation from the last partial interval up so till we get to our current value of X. So what is this? We sum up a bunch of K delta X's and then we add another K delta X. So in essence, this whole thing is just the sum of k delta x. How do things accumulate? Bit by bit by bit. Delta y plus delta y plus delta y plus delta y. So that's what this thing is doing. So this is a bunch of completed intervals summing up k delta x, and then plus a little bit more, plus k delta x a little bit more. So in essence, that AX formula is just summing bit by bit of change, bit by bit of change. Let's do it again. The total accumulation of Q from A to X means, what does it mean? The accumulation of Q across many completed or whole intervals, that's the first part of the equation. Plus, a little more accumulation for the partial interval. In essence, another k delta x. So it's just a sum of lots of k delta x's. Okay, hopefully this is helping. Any questions? All right, and then in recitation, we want to dig into the nitty-gritty of this. And we'll also kind of touch on that today when we do the example. But again, we need to know what's going on here. We need to know what's going on. This input into R. This input into R is important. Okay, so there it is. So we've got a context here. Get that handout out. I'm going to get that handout. Now, make sure you're on page 1. You know you're on page 1 because it doesn't say at the top, this is page 2. Begin on the other side. Okay? So make sure you're on page 1. So what do we got? We're unloading sand onto a scale. Okay, we're unloading sand on a scale. And this is the exact rate of change as a function of time. So over here, you might want to make the numbers a little bigger like I'm about to do here so you can see it. So this is 100 pounds per second, 200 pounds per second, 300 pounds per second, etc. Right? In hundreds of pounds per second, that's our rate of change. And then this is seconds down here. So the first one you can see is 0.5 seconds. 1 second. So this is our left and right graphs. We start with the left graph, which is showing now it's showing the exact rate of change of the weight of sand on the scale as the truck unloads. So just in general, how is the sand unloading? So at first, how is the sand unloading? Slowly at first, at a low rate, and then at a faster rate. So like you just imagine like a little bit trickling off, and then the truck bed gets a little higher, and then most of it comes off, and then what happens at the end? Slows down, then just a little bit, right? So you can imagine that, right? So a little bit, and then all of a sudden the most of it, and then a little bit more at the end. So that's kind of the idea of how this rate is starting at a slow rate, and then fast rate, and then slower rate. Okay? So, and then we're gonna, what's our goal? So our goal is to, in the end, we want the exact accumulation of weight. And that will be over here, and this will be hundreds of pounds. This will be hundreds of pounds. We want the function that at any time in seconds tells us the exact accumulation of weight at any time. So again, this is 100 pounds, 200 pounds, 300 pounds, 400 pounds, etc. And then this is the same time quantity, right? Our x-axis on both graphs are the same. That input quantity is the same. And we got rate of change on the left, on the y-axis, and total accumulation on the left, on the y-axis of the right-hand graph. So I think you're ready to go on page 1. Follow the instructions. So this is your chance to kind of fill in the gaps of what you haven't understood in the last couple of weeks. We're taking everything we've done in the last 2 or 3 weeks and applying it to this example. So here is your chance to understand what you haven't understood up to this point by applying it to an example. Work together, we'll come around and help. Okay, just work on page 1 for now. Don't go on to page.
Ax minus yeah, which is G, which is the y number, which is the and G.
Okay, check your number 2. Check your number 2. I'll put up number 3 in a second.
It's right of x, not left of x.
This is how you do. Oh, sorry, excuse me. Right of x, you have to do. This is the definition of right of x. Or sorry, yeah.
Yeah, so you can write that. Yeah. I like it.
Oh, so you just say, okay.
Yeah.
That's how
Yeah, I'm just saying.
that's how I wrote it. You said plus delta x.
Good for you.
Yeah.
Good for you. That's right.
Yeah, I just didn't play around.
If you just get the first 3 lines of AX, go on, right? If we get the first 3 lines right, then just move on. Don't. Once you get the pattern, then it's easy after that. So just get the first 3 lines. So you got to be careful because it's right. It's right. Plus what? Not R of 0.5. It's not plus R of 0.5. A, the total accumulation up to that point, not the rate. A of everything accumulated up to that point. What's everything accumulated up to that point? 1. Yeah.
Just the thing is this could be less than x, then less than 1.5. Just swap.
Yeah, thank you.
You know,
That's right. Yeah.
If we do R.5, what it'll do, it'll take left 5. And then, so anyways, the formula we have for it, I don't have it. Like, right of, well, I guess R of 0.5 works. But remember the issue we had last time, that if you did R...
That's why I changed it to right. So with right, it works. With using right sides, this works.
Okay.
Because you're always you've got the total accumulation from the previous one. So you've got, say, this can calculate A of 1,
Okay.
and that's what you're going to use to add onto this next time. It's when you have to do left, it doesn't work.
Okay.
But with right, it works.
Yeah, so R here is the exact right. Yeah, but anyways, because if we did right of 0.5, it would actually be 1.
Right?
Right of 0.5 is 1, even though 0.5 is on the interval. So it's good that we're not using...
No, right of
stuff.
0.5 is 0.5.
So that's what...
Because at the right side, you're taking all the rates you're taking all the x values in an interval and assigning them to the rate at the right side of the interval.
X.
Just like if you plugged in the left side of an interval into left x, you get it back. When you plug the right side of the interval into right x, you're going to get it back.
So if we did it right, it would be A, which is 0, plus delta x times x minus a, which is 0.5 minus 0, over delta x, which is 0.5. Take the floor. So this is 1 times 0.5 would be 0.5, and then we have that extra plus x to get to the right of the interval. Because without this, this would be left.
Okay.
And then we add delta x to get to the right, and that actually ends up being 1.
Oh, okay.
But
That's pretty solid.
anyways,
here.
it's just,
Oh,
yeah.
Okay, thanks. You're
As
right.
long as you're using capital R, like, it's fine, because you're just
Okay.
taking the rate at 0.5. But if somehow you were using y
Got
of
it.
x and calculating the rate,
Got
it would
it.
be confusing.
All right, let's see how you did on this. Do I have enough room? A, which is 0. X. Minus 0. Over 0.5. Plus right. It's right. So for right you need it's gonna be j, not j minus 1, right? Okay, r of left or r of right?
Right.
Times x minus what?
Right is right.
Right or left? Okay, so remember what that is. It's the rate, so it's the rate, r of right,
minus left.
times what? That little distance left in the partial interval. How do we calculate that little distance left in the partial interval? X minus left. It's the little distance remaining in the partial interval. Right's over here. It doesn't have anything to do with that distance here. You see? It should be, it's x minus left.
That will always be independent, right?
Yes, that's right.
That's the only part of the function that will never change.
Oh,
Are we gonna be able to keep these?
sure.
Thank God.
Come back, please.
Professor, really quick, are those twins?
No.
No.
In fact, they're the furthest thing from twins. They're adopted. They're both adopted.
I told you.
Do you understand why it's x minus left? Because it's the little bit remaining of that little bit of an interval. So it's going to be final value of x minus initial x to get that distance in the partial interval. Right is over here. It has nothing to do with that distance over here in the partial interval. Yeah. Using left, yeah. Delta times delta k delta x.
And then plus r of
Left of x.
times k minus right.
No. So it's
Or sorry, x.
x minus what? So to get to that last interval, we need the distance of that last partial interval. It's always x minus left. It's always x minus left. Last chance, questions on what? 1 through 3. Last chance, questions.
I'm so glad we're doing this.
Yeah, good.
I like these.
Okay, so now let's talk about, we've got the step, approximating step function. Can we get a general idea of what the approximate accumulation function will be like? I'm going to erase. Can I erase?
Please.
Going to erase. It'll all be on the video. Okay, so here we go. What's it going to look? I'm going to turn on the approximate accumulation function on the right side. So this is the accumulation. I'm going to turn it on. Here we go, because we got to move on.
That just gives me like,
How many got it? Who got it? Does the accumulation decrease? Does it ever decrease?
Negative.
Why not?
Because
Someone said it. The rate's always positive. If the rate of change is positive, your accumulation is going to be going up. And that makes sense, right? The weight unloads, the scale's just going to increase in its reading, right? The scale reading will increase the whole time. It just will increase slower at first, and then faster in the middle, and then slower at the end. So this is what the approximate accumulation function looks like. Okay, so now we got it. So page 2, I want to make sure we get to the end of page 2. That was what I really wanted to do. So page 2 now switches back to left with intervals of 0.3. But we're not going to write out the multi-line version anymore, okay? So you're going to do left with delta x of 0.3, and we're just going to use our one formula version of both step and A, okay? One formula version.
TikTok.
Oh, of course. Of course.
sweet.
Okay, really want to get to number 8. So skip to numbers. So 6 should be easy. Step X. How is step X defined now? As one rule, R of left of X. Okay, skip 6b, do it later, all right? It's an important question, but I really want to get to 8. Okay, so skip 6b.
Are we gonna hand in these handouts
No,
at the
it's
end
for
of
you.
class?
No,
We can keep them.
yes, it's for you.
Sounds good.
Okay, so here's the adapted version of A for this situation. Delta x is 0.3 and A is 0, right? A is 0 and delta x is 0.3, so that's what for the unloading sand, the weight of the sand becomes this. So what I want to do is I want to look at A of 1.4. How does it actually calculate, say, A of 1.4? So we're plugging 1.4 into this function. We want to break down piece by piece, how does it get A of 1.4? So how does it do it? So what we said, it's the sum of completed intervals, full completed intervals, plus a little more accumulation for the last interval. So we're going to do the sum of the completed intervals first. So what about the number of, so we're doing A of 1.4. So what about the number of completed intervals? So that would be the floor function, the 1.4 minus 0 over 0.3, which is 4.7, the floor of 4.7. And what's the floor of 4.7? 4. So we're gonna. This is gonna sum together 4 things. It's gonna go j equals 1 to 4, because that floor function of 1.4 minus 0.3. No, j equals 1 to 4. It's going to be 1, and then it's going to be 2, and then it's going to be 3, and then it's going to end at 4. It's going to end at 4. So j equals 1. Here we go. For j equals 1, what's the little bit of accumulation we get? We get r of 0 plus 0 times 0.3 times 0.3. This is for j equals 1. And that equals r of 0 times 0.3. Now, if we look back at the rate graph being formed over there, when j equals 1, what did this just do? It just did that rate times the interval, k delta x. You see, r of 0 times 0.3 gives us that little bit of accumulation for that step. There it is, r of 0 times 0.3. Okay, j equals 2. R of 0 plus 2 minus 1, or 1 times 0.3 times 0.3, which is r of 0.3 times 0.3. So now we're talking about the second full completed interval right here. What's the rate of change? R of 0.3, there it is, times delta x. 0.3 gives that little bit of accumulation for the second interval. J equals 3. R of 0 plus 3 minus 1 is 2 times 0.3 times delta x equals r of 0.6. What interval are we talking about now? J equals 3, third interval. What's the rate in the third interval? R of 0.6 times the delta x. 0.3 gives us the bit of accumulation for the third interval. One more to go. J equals 4. R equals a 0 plus 4 minus 1, 3 times 0.3, all times 0.3 equals r of 0.9 times 0.3. Again, j equals 4, fourth interval, right here. What's the rate of change? The rate at the left side, r of 0.9 plus 0.3. So then, what does it do? It sums up all of those when j starts at 1, and then 2, and then 3, and then 4. So it's going to sum up k delta x for j equals 1, k delta x for j equals 2, k delta x for j equals 3. How do things accumulate? Bit by bit. How do we calculate each bit? K delta x. All right, now there's the last thing. Here we go. We made it. Now we're going to do this. I'll do it in blue. So what is it? We're plugging in, we're doing a, this whole thing is to calculate a of 1.4. That's what we're doing. We're doing a of 1.4. That's what I'm doing down here. So for a of 1.4, there's four whole intervals. That first part of the sum sums up the k delta x for the first 4. And then we have a little bit more. How much a little bit more do we have? So I'm going to stop it over here at 1.4. Okay, there we are at 1.4. So the first part over here, just add it up, k delta x, k delta x, k delta, j equals 1, j equals 2, j equals 3, j equals 4. Now we have this last little part. So r of left of x is going to be r of left of 1.4. We're plugging 1.4 into the function. What is left of 1.4? 1.2. So it's going to be r of 1.2. And that's the rate of change. R of 1.2 is the rate of change in this last partial interval, or you could say the fifth little step, but it's smaller, right? And so how big is that step? Times 1.4 minus left of 1.4. So what's that? That's like our smaller delta x. 1.4 minus left of 1.4, which is, instead of times 0.3, now it's times 0.2, because this is 1.2. So here then is the little bit more accumulation, k delta x, for the little partial step there. And so this a of 1.4 adds up all 5 things. The left term adds up the first 4 whole intervals. The right term then adds on the little k delta x for this partial interval. And when you add all those up, you get A of 1.4, the total weight of sand accumulated at 1.4 seconds. Study.